Welcome to Tomorrow Unveiled, your weekly glimpse into the future as it unfolds. Today, we're taking a deep dive into the incredible surge of activity that defined beyond Earth this week in space news, specifically covering that pivotal period between September 5th and 12th, 2025. What's truly striking, looking at the developments from this past week, is that we're clearly moving past just sort of conceptual exploration in space. Our dedicated research team has identified this as a really critical transition point, a point where the tangible engineering of a sustainable off-world economy is truly taking shape. So our mission for you today is to extract the most important nuggets of knowledge from these recent developments. We're focusing on those foundational technologies that are now reaching critical maturity. And these aren't just small steps. They promise to redefine the economics of space operations and, maybe even more excitingly, dramatically shorten the timelines for deep space transit. We'll explore how these distinct yet interconnected threads are weaving together an accelerating roadmap for, well, permanent human and robotic expansion across our solar system. It's a truly exciting time.
It absolutely is.
Yeah.
And as we've seen, this acceleration isn't just about faster rockets. It's really about establishing the very building blocks for an independent space economy. We're really talking about technologies that enable independence from terrestrial supply lines and, of course, dramatically compress the vast distances of the solar system, making future ambitions genuinely attainable.
That's a perfect way to frame it. Okay, let's kick things off with what we're calling the foundational pillars of off-world expansion. I like that phrase. The underlying capabilities that make everything else possible. And first up in this category is advanced manufacturing and in-situ resource utilization, or ISRU. Now, we've seen a major breakthrough from Boeing this week, a new process for creating 3D printed solar array substrates for satellites. Okay, let's unpack this. A 50% reduction in build time is huge GE for satellite production. That's a game changer for getting constellations up faster. What are the ripple effects here? Cutting build time by maybe 6 months?
You've hit on the core of it. Yeah, 50% reduction isn't just, a nice number. It means constellations can potentially deploy twice as fast. Think about the implications there. It could lower market entry barriers for new space companies, letting them get their systems into orbit much quicker. Or it could enable existing players to just dominate with sheer volume. And this elegant approach, it consolidates dozens of separate machine components into basically a single monolithic substrate panel with integrated features. So that inherently simplifies assembly and, crucially, reduces potential failure points. This kind of leap in efficiency for such a critical component, it changes the calculus for an entire industry. And Boeing is actually targeting market availability for this new capability in 2026, which is remarkably soon.
Wow, 2026. That is soon. Okay, so that's a game changer for, let's say, the Earth-based part of satellite production, making things faster here. But then if we connect that to the bigger vision, the self-sustaining space economy, we also saw Blue Origin's Blue Alchemist system, their ISRU system. It successfully completed its critical design review this week. Now, this system is designed to produce oxygen, silicon, metals, directly from lunar regolith simulant. Can you break down what molten regolith electrolysis, MRE, actually is, and why this particular approach is so important?
Absolutely. Molten regolith electrolysis, MRE, it's essentially zapping moon dust, what we call regolith, with electricity at really high temperatures, usually around, say, 1600 degrees Celsius. And you do that to extract useful elements like oxygen, silicon, metals like iron or aluminum. Now, what's crucial about Blue Alchemist's approach is that it requires no water, it produces no carbon emissions, and it uses no toxic chemicals. It's an incredibly clean, environmentally friendly way to, well, live off the land on the moon.
Right. No water needed is a big deal on the moon.
A huge deal. And Blue Origin really emphasizes the profound economic impact here. Every kilogram of oxygen produced on the moon is one less kilogram you have to launch from Earth. And launching mass from Earth is incredibly expensive. So this is a major potential cost saving.
Yeah.
They're aggressively aiming for a fully autonomous demonstration of the end-to-end system. In a simulated lunar environment, mind you, but still aiming for 2026.
Another 2026 target, that's ambitious.
Very ambitious. But what's fascinating here is how these two developments, Boeing and Blue Origin, while distinct, they really converge, don't they?
Yeah, I see that. One makes the start faster, the other makes the end game possible.
Exactly. They converge in the broader strategy for building a space economy. Boeing's innovation optimizes the Earth-based supply chain, making that initial deployment faster, cheaper. Blue Alchemist, in contrast, is designed to ultimately eliminate that supply chain for critical stuff like power, propellant, air. Once the infrastructure is actually in place up there, it's strategic pivot From a logistics-dominated supply chain model to what you might call a capabilities-focused value chain model, building value in situ.
That's a powerful distinction, making terrestrial supply chains faster versus, well, eliminating them entirely where possible. How does that philosophical shift then influence the way we even think about moving through space? Because if we can build and fuel things on the moon, the next logical step is getting around the solar system faster, right? And that brings us to some, frankly, mind-blowing advancements in propulsion. Our research team detailed ongoing work at The Ohio State University on a novel nuclear thermal propulsion, NTP, concept. It's known as the Centrifugal Nuclear Thermal Rocket, or CNTR. This isn't your grandfather's NTP, is it? It uses liquid uranium fuel contained within rapidly rotating cylinder.
Yeah, it's a radical departure from the solid-core NTP designs we've seen tested before, like AirVia back in the day.
Right. And propellant like liquid hydrogen bubbles through this molten fissioning fuel. That sounds intense.
Yeah, it is intense. It allows for direct heat transfer at incredibly high temperatures, potentially up to 5,000 Kelvin, which is significantly hotter than solid-core designs can handle.
Okay, here's where it gets really interesting. The projections. Imagine cutting a Mars trip in half. A round trip in under 15 months. That's genuinely transformative. From your perspective, what's the most significant impact of that reduction in travel time? Beyond just, reducing crew radiation exposure, which is obviously huge.
It's truly revolutionary. And yes, reducing radiation exposure is critical, absolutely.
Yeah.
But the biggest impact might be on the entire architecture of human exploration. Think about it. A Mars round-trip mission that takes under 15 months compared to nearly 3 years with conventional chemical propulsion. That opens up vastly more mission profiles. It makes aboard-to-Earth capabilities far more robust, too.
Yeah.
Things go wrong, getting home is much quicker.
Point.
And psychologically, it's a game-changer for the crews. It makes those long-duration deep space missions much more viable, less isolating. The CNTR's Target-Specific Impulse, or ISP, which is basically, a measure of engine efficiency like miles per gallon for rockets. It says approximately 1,800 seconds using hydrogen propellant. Now, to put that in perspective for you listening, that's double the efficiency of previous NTP designs, which were around 900 seconds. And it's 4 times that of the best chemical rockets like the Space Shuttle main engines or RL-10s, which are around 450 seconds.
Double the previous nuclear concepts and 4 times chemical rockets. That's a staggering leap, not just incremental.
Exactly. It's a generational leap. And here's where it ties back beautifully to our earlier discussion about ISRU.
Ah, okay. How so?
Well, the CNTR's potential ability to efficiently use a variety of storable propellants, things like methane or ammonia, both of which are potential products of ISRU operations, especially on Mars or maybe even asteroids.
I see. So the engine could use fuel made in space.
Precisely. It means a propulsion system could effectively live off the land by using locally sourced propellants. This fundamentally changes the architecture of interplanetary transportation. It makes those lunar and Martian ISRU facilities, like Blue Alchemist, exponentially more valuable. They become not just resource outposts, but interplanetary refueling stations.
Interplanetary gas stations. Wow, that really connects the dots.
It does. It reminds me of, the early days of air travel. Every innovation, however small it seemed, had this compounding effect. These space developments feel like they're on a similar trajectory. It's all starting to link up.
It's about making space travel not just faster, but more flexible, safer, and ultimately, self-sufficient. This transition feels profound. And if you're finding this discussion insightful, maybe pause for a second if you're watching on YouTube. Please take a moment to like this video, subscribe to Tomorrow Unveiled, and maybe consider hitting that new hype button. It really helps us reach more viewers. And of course, turn on notifications so you don't miss our future updates. Okay, so we've got manufacturing breakthroughs, ISRU coming online, and revolutionary propulsion. Let's turn our attention now to the evolving marketplace. Launches, satellites, and orbital capabilities. The commercial space marketplace is definitely maturing at a rapid pace. We're seeing an evolving competitive landscape, expanding capabilities in orbit, and the growing strategic importance of space-based services. And we're seeing some remarkable milestones. For instance, SpaceX's 500th Falcon booster landing during a Starlink mission just this past week. 500 landings. That's not just a number, it's a testament to how routine booster recovery has become, right? And it's supporting this unprecedented launch cadence.
Indeed. We've seen, over 70 Starlink satellites deployed weekly, on average, over 2,000 deployed just in 2025 so far, and SpaceX is targeting over 170 total launches for the year across all customers. That kind of cadence reshapes the entire industry. It allows for rapid constellation deployment at scales that were, frankly, previously unimaginable.
Yeah.
But what's equally exciting, I think, is how this success is fueling the next wave of competition. We're seeing Rocket Lab aggressively advancing the development of its Neutron rocket. We've seen significant progress lately, the official opening of its dedicated launch complex in Virginia, Launch Complex 3, and successful hot fire testing of its Archimedes engines.
Those run on LOX methane, right? Liquid oxygen and methane.
That's right, a fuel combination that's gaining a lot of popularity for its efficiency, storability, and potential for ISRU production down the line, especially on Mars.
Ah, it connects back again.
Exactly. So this indicates they're moving swiftly from design into real hardware development. Neutron is designed to deliver 13,000 kilograms to low Earth orbit in its fully reusable configuration, and it features that unique captive payload fairing.
Right, the fairing that stays attached and just opens up like a clamshell. That's clever, so it's reusable too.
Precisely. It reduces mass, complexity, and improves reusability. Rocket Lab maintains a target of a first launch by the end of 2025. If they hit that, they'll introduce significant competition in the medium-lift launch sector, which is currently dominated by Falcon 9.
So having a second credible, reusable medium lift provider, especially from the Western world, that's got to be good for the market, right? Drive down prices, maybe?
Absolutely. It will likely drive down prices, offer greater scheduling flexibility for satellite operators, and, honestly, force further innovation across the board. That benefits everyone, from commercial satellite companies to government customers.
Excellent. More options, more innovation. That's great for the industry. And speaking of satellites themselves, let's explore how they're augmenting global capabilities. Communications and navigation seem to be key areas this week. We saw the successful deployment of 21 satellites for the U.S. Space Development Agency's, or SDA's, Tranche 1 transport layer. These are advanced military satellites. Our research team highlighted features like optical intersatellite laser links, basically super fast, secure fiber optic connections, but beaming through space, plus encrypted communications.
Yeah, these satellites are designed to provide global, low-latency tactical communications directly to warfighters. It marks the start of operational deployment for a new era of proliferated defense constellations. It's a really significant step in securing communication capabilities, especially in contested environments where traditional systems might be vulnerable.
Makes sense. But it wasn't just military applications making headlines, was it?
No, not at all. We also saw the successful launch of Indonesia's Nusantara Lima communications satellite.
Yeah.
This one was built by Boeing. It's a very high-throughput satellite, or VHTS, designed to provide a massive capacity, 160 gigabits per second. That's huge.
160 GBPs. And that's aimed at what?
Enhancing high-speed broadband internet, especially to underserved and remote regions across Indonesia's vast archipelago. More than 17,000 islands, I believe.
Wow, that's a truly vital service for connecting a nation spread across so many islands. Digital inclusion?
Definitely. And then on the navigation front, we saw Europe's space agency, ESA, officially announce the name of its Low Earth Orbit Positioning, Navigation, and Timing LOPNT demonstration mission.
Ah, yes, Celeste. Sounds elegant.
It does. This is a forward-looking initiative. It'll consist of 10 satellites plus 2 in-orbit spares, and it's designed to test how a new layer of satellites down in LEO can enhance the resilience, accuracy, and availability of Europe's existing Galileo navigation system.
Which operates in medium Earth orbit, MEO, right? Like
Yeah.
GPS.
Exactly. So this raises an important question. Why are we seeing this dual approach? You've got these powerful, centralized geostationary GEO satellites like Nusantara Lima, providing massive bandwidth. And then you have distributed LEO constellations like Celeste, or Starlink for comms, or SDA for defense.
Different tools for different jobs? Or something more?
I think it suggests a strategic shift towards integrated multi-orbit networks. You get resilience, you can serve diverse market needs. You're not relying on just one orbital plane or a few really high-value assets.
So redundancy and tailored services.
Precisely. And the first 2 Celeste satellites are scheduled to launch in the coming months. It highlights a critical commitment from Europe towards strategic autonomy and hardening their vital PNT infrastructure against threats like jamming and spoofing. It's about redundancy and robustness, something we often see, in the evolution of any critical infrastructure.
Absolutely. It's not about one type replacing the other, but building a more robust, layered system overall. Very interesting. This leads us nicely into our next major theme, building the orbital economy. the actual space infrastructure. Because beyond the launch pads and the satellites themselves, a new generation of in-space infrastructure is being planned. Stuff to support a permanent and thriving human and commercial presence in orbit and, eventually, beyond. I've been watching NASA accelerate its strategy here. They need to ensure there's no gap in America's ability to maintain a human presence in low Earth orbit after the International Space Station, the ISS, is deorbited in 2030. And they just released a draft announcement for partnership proposals for Phase 2 of this program. It's been rebranded now as Commercial Destinations Development and Demonstration Objectives, or C3DO. So what does this all mean for the future of living and working in space? I mean, it feels like a huge shift, doesn't it? From purely government-led infrastructure to commercially driven habitats, with NASA basically acting as an anchor tenant.
It's absolutely a pivotal transition. It signals a maturing space industry where commercial entities are genuinely expected to take the lead in developing and operating orbital infrastructure, not just supplying parts, but owning and running the place. NASA expects to make somewhere between $1 billion and $1.5 billion in funding available between 2026 and 2031 to support a minimum of 2 separate companies.
Okay, 2 companies minimum. And what do they have to deliver?
The requirement is pretty demanding. They must culminate their development with an actual in-space crewed demonstration. We're talking 4 astronauts for a minimum of 30 continuous days, living and working on their station. And this has to happen no later than 2030.
Wow, 30 days with 4 crew by 2030. That's a serious deadline.
It is. And interestingly, this transition uses flexible Space Act agreements, SAAs, instead of traditional contracts. This gives the companies more latitude in how they design and build, but it also means they need to bring significant private investment to the table. NASA's funding won't cover the whole cost.
Right, it's seed money, essentially.
Exactly. This isn't just about building a new station. It's about building a whole new economic model for how we operate in LEO.
A completely new model, indeed. And while these plans for future commercial stations are advancing, the ISS itself remains really vital, right? It's still a unique platform for research and tech development.
Oh, absolutely. We saw that underscored this week with the recent Northrop Grumman resupply mission. It delivered a host of science experiments and technology demonstration payloads.
What kind of things?
Well, there was Voyager's Space Edge, which is basically bringing cloud computing infrastructure to orbit, making data processing faster and more autonomous up there. There was also Transastra's Capture Bag, a novel inflatable system designed for capturing and deorbiting space debris, which, as we'll discuss, is becoming increasingly critical.
Yeah, definitely need solutions for that.
And also ongoing commercial pharmaceutical research. Things like protein crystal growth experiments, which leverage microgravity for potentially groundbreaking drug development down the line. So these current ISS activities, they're directly informing the capabilities needed for those future commercial stations and even deep space missions. It's bridging the gap between today and tomorrow.
That blend of current research and future development is really powerful. It shows the ISS is still pulling its weight even as we plan its succession. And speaking of going beyond LEO, let's touch on NASA's fast-tracked plan to deploy a 100-kilowatt nuclear fission reactor on the moon. Also by 2030. That sounds truly audacious.
It is audacious, but potentially necessary for sustained presence.
Right, because this would provide continuous electricity through that long 2-week lunar night. It's not just about keeping the lights on the habitats, is it? What does this unlock for sustained lunar operations that solar panels simply can't provide?
Yeah, this is a fundamental shift in capability on the lunar surface. Solar panels are great, obviously, during the lunar day, but that 2-week lunar night, temperatures plummet to extreme lows, and you have zero solar power. A fission reactor provides continuous, reliable power. Enough to run habitats comfortably, yes, but also power-hungry equipment like drills for resource extraction, crucial for that ISRU we discussed earlier.
Ah, powering the moon mining operation.
Exactly, and powering extensive scientific outposts. It means you could have operations running 24/7, 365, 24 lunar day-night cycle, even through the long, cold night. That continuity is essential for any kind of permanent human presence or serious industrial activity. This is clearly seen as a strategic move for a sustained U.S. foothold on the moon, a foundational piece of infrastructure for whatever comes next there.
It's hard to overstate the importance of reliable, consistent power for any kind of sustained human settlement anywhere, whether it's Earth or the moon. Okay, so we've covered a lot of incredible progress and ambitious plans, but as always, it's vital to explore the other side of the coin. navigating the future challenges and considerations. Despite all these optimistic announcements, formidable hurdles remain. Technical ones, programmatic ones, regulatory ones.
You're absolutely right. It's important to keep perspective. First, let's talk technical and operational hurdles. Scaling ISRU, like Blue Alchemist, from a terrestrial lab environment to an autonomous operational plant on the actual lunar surface. That presents monumental engineering challenges. You have to deal with regolith variability. Moon dust isn't uniform. Handling it is tricky. Extreme thermal management in a vacuum is tough, and achieving autonomous reliability in that incredibly unforgiving environment, it's a huge leap.
Right. Lab success doesn't always translate easily.
Not at all. And for nuclear propulsion, that centrifugal nuclear thermal rocket, the CNTR, it faces immense obstacles because it's still at a very low technology readiness level, or TRL. Basically, it's early days. It requires cutting-edge material science just to contain molten fissioning uranium at thousands of degrees Celsius, safely, reliably. And then you have the complex safety and regulatory approval processes for ground testing, let alone launching something like that. These aren't minor issues. They require genuine breakthroughs.
Okay, significant technical hurdles. And beyond the tech side, what about the programmatic and budgetary risks? You mentioned that unyielding 2030 deadline for ISS deorbit. That feels like a major programmatic risk, doesn't it?
It absolutely is. Any substantial delay in the C3DO program, getting those commercial stations up and running, could result in a LEO gap, a period where the United States has no human-tended platform in low Earth orbit.
Which would be a major setback.
A huge setback. And the C3DO funding, while substantial, that $1 to $1.5 billion, is not enough on its own to cover the multi-billion-dollar cost of developing and launching these new space stations. So success is really contingent on sustained and predictable government funding, yes, but equally on attracting significant private investment to actually close that funding gap. It's a massive financial undertaking for these companies.
A public-private partnership where both sides really need to deliver.
Exactly. And the challenges don't stop there. We also have to consider orbital congestion and space debris. We touched on this. The relentless pace of satellite deployment, especially these large constellations, leads to increasingly crowded orbits.
More traffic up there.
A lot more traffic. And while we see potential solutions emerging, like Transastra's capture bag demonstration on the ISS, the urgent need for active debris removal technologies and robust space traffic management protocols is lagging behind the deployment rate. This creates real potential collision risks, which could create even more debris. And it also leads to radio frequency interference issues. It affects everyone operating in space, not just the new players.
So the question becomes, can we innovate the solutions faster than we create new problems in orbit?
That's the critical question for sustainability, yes.
And that sustainability question touches on regulatory and environmental conflicts right here on Earth too, doesn't it?
Yeah.
Our research team noted issues like spaceport expansion, SpaceX's ambitious plans to double its launch rate at Vandenberg Space Force Base in California, for example, facing environmental scrutiny and opposition from local regulatory bodies like the California Coastal Commission.
Right, and that highlights the ongoing challenge of balancing the technical needs and desires of rapid space development with very real environmental impacts and public concerns back on the ground.
It's a complex interplay.
It absolutely is. These challenges, as you said, they aren't just technical hurdles to overcome.
No, they're societal, they're economic, they're geopolitical, they require international coordination, new regulatory frameworks, thoughtful governance, basically, to ensure space remains a sustainable and safe domain for all humanity, not just the first few players. Thoughtful governance, that seems key. And we love hearing your thoughts on all this. Whether you're listening on YouTube or your favorite podcast app, please leave a comment and let us know what you think about this week's space news, these challenges, and the future of humanity beyond Earth. What are your main takeaways or concerns? If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners interested in these topics. So, wrapping things up, the developments of this past week, they paint a really encouraging picture, but also a challenging one, of our near-term future in space. It definitely highlights a convergent roadmap emerging towards, potentially, a multiplanetary economy. Our research team's findings show us an extraordinary momentum in space technology right now. The coming years, the rest of the 2020s, will be a crucial testing ground for our ability to manage and mature these innovations responsibly. We are witnessing the simultaneous and parallel maturation of those three foundational pillars needed for a self-sustaining off-world presence. 1. Sustainable habitats and infrastructure. 2. In situ resource production. And 3. Efficient and rapid interplanetary transportation.
That convergence is key. seeing progress on all three fronts at the same time.
Exactly. And the convergence of these critical technologies on roughly a 5 to 10 year timeline, it strongly suggests that the 2030s could genuinely be the decade. The decade in which a permanent, economically driven human presence beyond Earth transitions from strategic planning documents into operational reality.
It's an inspiring vision, definitely. But it leads us back to that fundamental question, perhaps the most important one. Will the incredible pace of innovation and private investment ultimately outstrip our ability to responsibly govern and manage this burgeoning space economy? Or will collaboration, foresight, and, as you said, thoughtful governance ensure a truly sustainable and equitable tomorrow unveiled beyond Earth for all?
A truly provocative thought to end on. Can we innovate faster than we create problems, and can we manage the frontier wisely? Thank you for joining us on Tomorrow Unveiled. We look forward to exploring the future with you again next time.